you'll either be in shift or load in such a case that when the clock's being used, the other one will actually not respond to the clock anyway. So what we've got, in one mode, when we're driving these clock pulses, we want the clock to drive this to read the information in, but at the same time we don't want the clock to be messing up these shift registers down here, I suppose.
Is this just, instead of having it all data chained in one line?
This is because we're wiring up, we're using this both as for inputs and for outputs at the same time. But what we don't want to do is if we're reading in a batch of the inputs, the clocks which are being driven out to read that in. We don't know which clock pulse is affecting the outputs and doing anything with that at the same time.
So one is set specifically for outputs, one is set specifically for...
So this half of it is only for the outputs. And one setting will be such that this will be active and the other will basically be in its kind of locked state. And in the other state, this will be kind of not doing anything, and then this will be actively responding to clock pulses,
so
but not both at the same time.
They're not bi-directional?
No, they're not bi-directional, not in the slightest. I'm not aware that, well, you may be able to buy some kind of bi-directional shift register type things, but these are the CPOs and these are PISO, so this is serial in parallel output and the other arrangement. But no, up there is only about inputs and down here is only about outputs. I wouldn't expect you in an exam, for example, to be able to draw a diagram like that. This just happens to be a practical implementation that's from a textbook. What I would expect you to be able to do is something like this. Like I say, I'm not sure you need those latches there because, oh damn. But, so if you've got latching shift registers, you could just simply get away with this being the outside world here. You do need a latch pulse though to sort of latch what it sees, and then enable the shift and read the information in. And in the other case, this arrangement, where you've simply got your shift registers again. What the crucial difference here is we're definitely going to need these latches, because as we're shifting the data through, we don't want that shifted data to be seen by the outside world. We only want it once it's all reached its final destination. So during the shift operation, the latches are holding on to the previous value of outputs, and they're ignoring what's going on. But once you've completed the shift operation, at that point in time, you copy across from what's in the shift registers to the latches, and then they become the new set of outputs. Okay. Let's quickly start today's topic. Right, first of all, so this topic is about basic input out, basic interfacing again. And this is just a reminder up here about TTL, that for an input, if an input is above 2.4 volts in classic TTL, that would be interpreted as logic 1. If it's below 0.9 volts, it would be interpreted as logic 0. If an input is in a voltage range between 0.9 volts and 2.4 volts, it's not clear what it will be interpreted as. The microcontroller will choose either a 1 or a 0 representation of it. It will say it's logic high or logic low, but it's not guaranteed which of those two it will choose. So generally speaking, when you're reading something in from the outside world, you don't want that voltage to be in the range 0.9 to 2.4 volts, because it's a kind of a voltage range that has no specific meaning for TTL logic. It's not clearly a 1 and it's not clearly a 0. So we have to engineer things to be either greater than 2.4 volts or less than 0.9. Another thing here is, unlike CMOS, traditional CMOS, if I have a pin on something like an 8051 and I don't connect it to anything, generally speaking, you can think of internally as a little resistor, so it's it's considered to be a logic 1. If you were to read a pin that's not connected to anything, generally speaking, you should read a 1. Okay? But this arrangement where you're not connected to anything, we regard it as floating. And there could be some kind of electromagnetic noise or something that could induce, I know you might think it's unlikely, but it could induce a current in here or something, so that actually it might put the voltage, a potential difference in here, such that it is that range, 0.9 to 2.4 volts. So you might not necessarily, if you read that pin, if it's floating, read logic 1. Most of the time you will. But it's good design practice to assume that it could go wrong. So if you have a number of inputs that are not being used or anything, well, they're not currently connected to anything, and if you want to read them, you would like to, I don't know, if they're unused, what we would normally do is we would wire them up through a resistor to a certain voltage. So we don't allow them to float. We actually, we determine precisely, we force them into a state. Because just leaving it unconnected, most of the time when you read it, you probably read a 1, but you may not read 1. You might read a 0, depending on if there's some kind of electromagnetic noise around. Now, you might say, I can't be bothered. I'm not going to have these external pull-up resistors. Well, that's up to you. If you're using, say, 6 pins on a port, reading it into the accumulator to process, but 2 pins are floating, and you're doing some kind of comparison, then depending on what's happened to those floating pins, it might have an influence on what happens as a consequence. Now, you could get around that by saying, well, I'll do masking, I'll mask out the values of those pins. Yeah, that's one solution. Another solution is to use external pull-up resistors. But anyway. So the term floating means that you have an input that basically isn't connected to anything. And if you were to read a floating input, generally you'd read it as a high, logic 1, but don't rely on that. It's not guaranteed. Another thing it's different between CMOS and TTL. In traditional CMOS, due to the technology involved, if you had any static electricity on you and you touched the pin, you had the possibility of actually blowing up transistors inside the device. That was known as zapping. Static electricity can actually cause, if you like, a charge build-up on a transistor, and then a spark to occur, causing it to destroy the transistor. TTL has what are called clamping diodes built into the inputs and outputs to protect them from that kind of thing. So generally, if I've got a cheap nylon carpet and I'm walking around with TTL logic, it's not going to do any damage. But a lot of you, when you're buying your devices for your design and build and things, if they come in static sensitive little packaging, and it says it's electrostatically sensitive, then don't just take out the packaging and walk across a nylon carpet, because when you touch it, chances are you'll destroy it. That process of destroying it because of basically the little spark that occurs from static electricity is known as zapping the device. In fact, if you're using certain types of devices which are electrostatically sensitive, you're supposed to wear an earthing strap around you so that there's no potential that's building up between you and the device you're touching. Anyway, that's got nothing particular to do with this course, just to be aware of it. But like the TTL, the good news is, because of these clamping diodes, usually we don't have to worry about static sensitivity. Right, here's the first. This is showing you various ways of wiring up an LED to a pin on a microcontroller. So we've got 3 basic ways of doing it here, and let's talk about each of those. Right, circuit A, effectively you would have this pin at a high potential, and then the other end of this LED is connected to ground. The potential difference will cause a current to flow through this, the LED will illuminate. There are 2 downsides associated with this. Downside number one is there's no current limiting resistor in series with this. So if the microcontroller was able to deliver a large current, this could basically damage the LED. And in fact, the LED will have almost no forward Hom resistance, so you might end up damaging the transistor inside here as well. So now in practice, if you were to do that, chances are it won't destroy the device, because at least in terms of the 8051, its ability to source current is actually very low anyway. So even if you were to wire it up like this, it's not likely to light up very brightly, but it's not good practice. Okay? Not good practice because in this arrangement here, between some hypertension in here and ground here, there's no resistance in series to limit the amount of current that's flowing. But also, this is not able to source, that's the technical term for it, it's not able to source much current anyway. Here's another arrangement. In this arrangement, effectively, in order to make this light up, we have to make the pin go low. Okay? By making the pin go low, we have current flow through here, and we talk about sinking a current. So this is an 8051 or a pin sinking a current as opposed to sourcing a current. Most microcontrollers are capable of sinking a bigger current than they can source. So it might only be able to source 1 milliamp, but it might be able to sink 20 milliamps safely. This is not a good arrangement either, though, because as we've got here, we've still got no series limiting resistor. So the amount of current that flows through there is only governed by whatever internal logic's going on inside here, and I don't know what that is. It's not particularly a safe thing to do. So C is the normal way we wire up LEDs to a microcontroller. That's the safe way of doing it. Where now we're using the microcontroller as a sink of current, and it can sink quite a lot of current, and we've got a series limiting resistor with the LED. So not too much current is going to flow into the microcontroller, not so much as it's going to overheat and damage any transistors. So C is the preferred way to wire up your LEDs. Generally speaking, if you want to do something sort of quick and dirty, doing something like this, you can get away with it most of the time, but it is a little bit risky. This is the elegant solution to how to wire up an LED. The problem here is we're still limited by how much current a microcontroller can sink. That's one problem with this. The other thing is to make the LED come on, we've obviously got to make the pin go low, so it's kind of counterintuitive. When you write a 1 to this pin, the LED goes off. When you write a 0, it goes on. So here's a couple of other arrangements that you could have using transistors. So now the microcontroller is connected to the base of these transistors. In this particular arrangement here, effectively when we switch on this transistor by driving a small current here, and it can be quite a small current to switch on the base of a BJT, then effectively the main current flows through the series limiting resistor, the LED, from the collector through to the emitter and ground. So you can use the microcontroller to drive quite a large current that way. The downside is you've got more components outside the microcontroller. That way, when the pin goes high, the LED comes on. If you do want it the other way around, you can use this arrangement. So in this arrangement, when the pin's high, this is on, the current flows through the limiting resistor, through the transistor down to ground, and the LED's off. When you switch the transistor off, then you end up with just this circuit, and so the current will just simply flow through the series limiting resistor and the LED. The assumption is that when the transistor is on, its resistance is much lower than the resistance effectively. You've got a barrier potential and things like that anyway. So given the barrier potential and things like that, this will work. That's one way of when this goes low, this comes on. When this goes high, this comes on. So there's a series of ways of wiring up LEDs to a microcontroller. Not a good way, but it would be brighter. A good way that's both bright and safe.
When you're doing A, when you can damage a chip by sourcing too much, is that because it's trying to like overdrive itself?
Yeah, the size of the transistor that's being driving the current, it'll be quite small. That charge flowing through will make it get hot. And I suppose that if this has got a very low resistance, the amount of current that's going to flow through that transistor internally here is more than it can safely think. It will get too hot and it will be damaged. I've done this. I have done A occasionally, but it isn't considered the best way to do things. If you're never sure about these things, one test you can always do with any chip that you are dealing with, you put your finger on the back of it. If you can't keep your finger on the back of it, it's that warm, you're in deep trouble because it really shouldn't be getting that hot. An ordinary chip, there are, but something like a microcontroller, under normal operation, it shouldn't be getting warm at all. So if it is getting warm, basically there's too much current flowing through a place where it shouldn't be flowing. I'll just do one more slide and we'll call it a day. I talked about this many weeks ago, but it's just to kind of remind you. This is showing you why the 8051, the pins are bidirectional. They can be inputs or outputs. If you have an 8051 pin that you've used as an output and then you want to use as an input, you have to be a little bit careful. If it's an 8051, it's always as an input, it's not a problem. But if it was previously used as an output and then we're going to use it as an input, you can end up with a situation like this. This is showing you what a typical, what's behind a port pin inside the 8051. So, let's say that previously we've written a 1 to this pin as an output. So Q is latched high, not Q is low, which means this transistor's switched off. That's okay. And so, if then you choose to use this input, this pin now as an input, and you happen to connect it to VCC, it's not particularly a problem because no current is going to flow through this transistor because it's been left in its safe off state. Because the last thing we wrote to this port pin was a 1 into the D latched into the Q, so the not Q was low, switching off the transistor. So that's the safe way. If, however, the last thing you had written to this port pin before using it as an input, so while it was an output you wrote 0, then what would happen is the D would be 0, locked into Q. The not Q will be high, meaning this transistor's on. Now while it was an output, that was fine, because as an output, you basically wired this pin to ground through the transistor, which is what you wanted to do as an output. You wanted it to be low. But now you've finished with it being an output, and now you want it to be an input, and someone comes along, some bright spark, and immediately wires up the pin to VCC. Under this situation, because the way this has been left, this transistor's been left switched on, now we basically have a pathway from VCC through the transistor, no limiting resistor whatsoever, straight through to ground. Within a very short time, this transistor will blow up, and then the port pin's dead. You've lost control of the port pin. So, if you're using pins just as inputs, and that's all they're going to be, it doesn't matter. If you're using a pin that under some conditions is an output, and then it's an input under other conditions, before you start wiring it up to things as an input, the last thing you should write into that pin should be logic 1, which is to make sure that this transistor is switched off. And that's why you often see in someone's code for an 8051 that kind of bizarre thing where before they've actually configured and done anything else, you see them writing 1s to all the port pins. It's the designer, it's the engineer playing safe to make sure that absolutely all the transistors have been switched off before they do anything else. Okay, so next week we've got a little bit more on this to do. I'll come back with that query on the that ship register thing. So we've got this to finish off, so that's the end of the displays in the matrix keypads, and then we've got the analog interfacing, and we should easily finish all of that in time, so it should be fine.
Sweet.
Okay, well have a good weekend.
Thank you.